before we look at a more general form, let's look at a specific example. Okay, we have, let's say the equation 4x squared plus 9y squared minus z squared equals 36. So that a would be 4, b would be 9, c would be -1, and d would be 36. And let's just look at this equation in the plane z equals 0. Now, in that plane, we get 4x squared plus 9y squared equals 36. Putting this into standard form, we get x squared divided by 9 plus y squared divided by 4 equals 1, simply dividing both sides by 36. Now this would be your a over d, and this would be your b over d in the previous, but you see that those are just going to be numbers and you're going to get numerical results in most cases. So what is this? This is an ellipse. And let's consider what that ellipse looks like. This is an ellipse. Graphing this ellipse in the xy plane. If you recall the means of graphing an ellipse, you remember that we construct a box that's okay, let's back up for just a second and let's put this into the form x squared over 3 squared plus y squared over 2 squared equals 1. Now this is the form x squared over a squared plus y squared over b squared equals 1. Something you should be familiar with. And again, if you're not familiar with this, you need to review as instructed earlier in the course. We move 3 units from the origin in the x direction, 3 units in the y, in the positive x direction, 3 units in the negative x, 2 units in the y direction, 2 units in the negative y direction, and we construct a rectangle. That's 6 units by 4 units. And the ellipse is simply going to be the elliptical shape that you get if you inscribe an ellipse in this rectangle. Now that's going to be like so, and thus, and not real well drawn, especially over here, but right there's the ellipse. So there's the graph of the ellipse. You should also know that if it's a hyperbola, we're going to draw the diagonals and decide which of the 2 sides, right and left or top and bottom, contain the vertex, the vertices, and draw the hyperbola accordingly, asymptotic to the diagonals through the vertices. Now, and you can tell that we would have a hyperbola. For example, if the 4 was negative, we'd have a negative here. That would dictate a hyperbola. And it would dictate a hyperbola with vertices on the y-axis. If the 9 was negative, we'd have a negative here. We would have the same picture, but the vertices of the hyperbola would be on the x-axis. Be sure you understand everything I just said. Now, there's the ellipse. How do we draw that? How do we represent that on a 3-dimensional picture? If this is x, this is y, and this is z, what do? Well, the same thing we did here. We mark off 3 units on the x-axis, 3 units on the negative x-axis, 2 units in the y-axis in both directions from the origin, and we sketch the corresponding rectangle. Now, the sides of the rectangle are going to be parallel to either the x-axis or the y-axis. The sides parallel to the x-axis are going to go through these 2 points, so we're going to have to draw these 2 sides. Well, let's just draw a dotted line parallel to the x-axis through this point, and another dotted line parallel to the x-axis through this point. Then let's draw a line parallel to the y-axis through this point of the x-axis. Here we go. And a line parallel to the y-axis here. And I'm not sure I really got good parallels, but you should understand what I'm getting at. And we can then fill in this rectangle and slightly correct any lack of parallel. So we can see this rectangle as represented in the XY plane. We can then sketch our ellipse. It's going to be here and come back here, and the ellipse is going to be tangent to the horizontal, to the horizontal or vertical, or the edge of the rectangle it encounters at the axis. So it's going to come around like this, like this. It's going to come around here like so, and back here like so. So there's not a particularly good representation of the ellipse in the x direction, in the xy plane, but we understand this is an ellipse in the xy plane, and that ellipse, any point on this ellipse, satisfies this equation, because for any point on this ellipse, z is 0 because it's in the xy plane, in the z equals 0 plane, and because x and y satisfy the equation we get if we let z equal 0. So we have this ellipse as part of the solution to this equation. Now we're going to go on and look at a plane that's above the xz plane, the xy plane, and see what happens there.